Up to this point, we've only looked at derivatives of two trig functions. We found that the derivative with respect to x of the sine of x was the cosine of x, and the derivative with respect to x of the cosine of x was a negative sine of x. Now that we have talked about the product rules and the quotient rule, we can find derivatives of the other trig functions. So let's start with trying to find the derivative of the tangent of x. Now the tangent is one of those trig functions that can be rewritten, and we could rewrite that as the sine of x over the cosine of x. And now that we know the quotient rule, we can fairly easily find the derivative of the tangent. So let's use the quotient rule. If our function is the tangent of x, then we know that the derivative of the tangent of x is the same as the sine of the cosine. So if we use this and the quotient rule, we can find the derivative of the tangent. So we have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. So we have cosine squared x, and this negative plus this negative becomes a positive, plus the sine squared x over the cosine squared x. And so cosine squared plus sine squared is 1 over the cosine squared x. And if we simplify that, we get secant squared x. So we can see that the derivative with respect to x of the tangent of x is equal to the secant squared x. We could go through the same process with the cotangent, but the derivative of the cotangent, and you would come up with this answer if we went through the same process that we just went through with the tangent. The derivative of the cotangent of x, which remember could be rewritten as the cosine over the sine, is equal to a negative cosecant squared x. So we just have two derivatives left to find for the trig functions. Okay, let's think about the derivative of the secant x. I can rewrite the secant as 1 over the cosine of x. And if this is going to be my function and I want to find the derivative, I cannot, in this case, use cosine x to the negative 1. That involves a rule called the chain rule that we haven't talked about yet, but we can use the quotient rule. So if I take the derivative using the quotient rule, we'll have the denominator times the derivative of the numerator. Remember that the derivative of any constant is 0, minus the numerator times the derivative of the denominator over the denominator squared. And this is going to be sine x over cosine squared x. But we're not going to leave it that way. We know that this is the same thing as saying 1 over the cosine times the sine x over cosine x. And 1 over the cosine is the secant x, and sine over cosine is the tangent of x. So the derivative of the secant is secant x tan x. The secant x times the tangent of x is the derivative of the secant. We could go through much the same process to find the derivative of the cosecant of x. Excuse me. Remembering that the cosecant is 1 over the sine. If you went through that process, you would come up with a negative cosecant x cotangent of x. So now we have derivatives of all of the 6 trig functions, and yes, you do need to learn these derivatives. Okay, here we have a function, and if we take the derivative of this function, it's fairly simple. There's no product rule, there's no quotient rule involved. It's just y prime is equal to the derivative of x is 1, and the derivative of the tangent of x is the secant squared of x, and that's all there is to that one. Let's look at one that requires the product rule. Y equals x times the secant of x. Now notice we have one function times another function, so we have to use the product rule when we find this derivative. So the derivative of y with respect to x, remember that's the same as y prime, it's just another way to write the derivative, is the first term times the derivative of the second term, which we found out was the secant x times the tangent of x, plus the second term times the derivative of the first term. So if we look at this, notice we have a secant x in common. I can factor that out, and we would have x times the tangent of x plus 1 as the derivative of x times the secant x. Whenever we are simplifying a derivative, we need to be sure that we combine all like terms and that there are no negative exponents in our final derivative. Now here I have a function, and I can find the derivative of this function using the quotient rule, or I could simplify the function and find the derivative, and we're actually going to do it both ways so you can see that they have the same value. I can simplify this function. It becomes 1 over the sine of x, which is the cosecant of x, minus the cosine over the sine, which is the cotangent of x. Now, these two functions represent the same function. If you were to graph, put both of these in your calculator and graph them, you would get the same graph. But we are going to look at the derivative 2 different ways. And I'm going to draw a line, kind of like we used to do with the trig proofs. And we're going to find the derivative using the quotient rule, and then we'll find the derivative of the simplified function. So if we start with the derivative using the quotient rule, I'm going to have the denominator times the derivative of the numerator, which is going to be a negative sine of x, which is a plus sine of x, minus the numerator times the derivative of the denominator. So here we get, and this was not plus the sine of x, it was times the sine of x. And it's too late for me to change that. So we have sine squared, whoops, and I forgot, all over the denominator squared. So let's go over that again. The sine of x times the sine of x, which is the derivative of the numerator, minus the numerator times the derivative of the denominator, which was a cosine of x. So in the numerator, I have sine squared of x minus cosine of x. That one's just by itself, minus the cosine of x, plus the cosine squared of x, all over sine squared of x. And sine squared plus cosine squared is 1. And we could simplify this just a little bit further. 1 over the sine squared is the cosecant squared. Minus cosine over sine is the cotangent, and 1 over sine is cosecant, so cosecant x, cotangent x. Okay, these are both good forms of that derivative. I would probably accept either one, but you need to recognize that this line goes to this line. Multiple choice, it could show up either way. Now let's work on the other side and see what happens if we take the derivative. The derivative of the cosecant we learned was negative cosecant x cotangent x, and the derivative of a cotangent, of a negative cotangent, would be minus a negative, which becomes plus cosecant squared x, which is the same thing we got there. I could rewrite it as the cosecant squared x minus cosecant x cotangent x. And you can easily see that whichever form of that original function you decide to use, you can get the same derivative function. Now we learned that velocity is the first derivative of the position function, and acceleration is the first derivative of the velocity, or the second derivative of the position function. Your second derivative is a higher order derivative. And you find the second derivative from the first derivative, just like we found the first derivative from the function. But if our first derivative is expressed as y prime or f prime of x or dy dx, these are just different ways we can express the first derivative. You might see it as the derivative with respect to x of f of x. The second derivative, we show 2 marks, y double prime, or f double prime of x, or possibly this way. That represents the second derivative, or maybe even this way, d raised to the second power dx squared of f of x. That just signifies to you that you want the second derivative. Some functions have a third derivative, and we use 3 marks here. F triple prime designates the third derivative. d3y over dx to the third, or d3 over dx3 f of x. If we had a fourth derivative, we quit doing the little tick marks and we would just have y to the fourth, f to the fourth of x, d to the fourth y over dx to the fourth. Or I think you can see the pattern here that's beginning to emerge. Or even just the nth derivative. Now we just use whatever that n is. D to the n y over dx to the n, or here. These are most of the possible ways that you might see a higher order derivative requested. Okay, here I have a second derivative, and I want to find the third derivative. So the first thing I'm going to do is rewrite this second derivative so that I have a negative exponent instead of a fraction. That way I don't have to use a quotient rule. And if we find the third derivative we just take the derivative of the second derivative. The derivative of 2 is 0. And we use the power rule. -1 times -2 becomes a positive 2. X, -1 minus 1 is -2. We never leave negative exponents. So we'd have 2 over x squared. If we wanted to take the fourth derivative, we would use this form, and it would become -4x to the -3, or -4 over x cubed. And you could keep going on and on as many times as you needed to.